Hello everyone, I welcome you all to this lecture. In this lecture, I am going to discuss IEEE 754 standard for floating point number representation. So let's discuss it. It is one of the very important topic. The very first thing we need to understand what is the need of any standard form. This form has been given by IEEE, that is Institute of Electrical and Electronic Engineers, and this was given in somewhere in 1985. Since then it is quite popular to represent floating point numbers. So if I consider any common number, let's say a number in decimal, so if I write, let's say 2, 3, 1, 0, 0, 1, 2, 5. Right? Generally, we do study in the previous classes, very early like 6th, 7th standard. These numbers we can represent in standard form. So if you represent this number in the standard form, we generally write like this, and considering this number in decimal, we write something like this: 1, 0, 0, 1, 2, 5. If it is in decimal, then we write 10 to the power. So how many places? 1, 2, 3, 4, 5, 6, 7, like this. So this thing we consider as the standard form, right? Similarly, for floating point numbers, if I take one example of any floating point number, the floating point number, like if I consider 0.000101101, if this is the floating point number, and let's say I am considering this thing in binary, okay? So if we want to write this, we can write this number as in a standard form: 1.01101 01101, and this is in 2 to the power. So how many points you are shifting this point? There are 1, 2, 3, 4 places. There will be -4, because this point is, we are shifting right direction, right? So this is easy thing you can understand. So we prefer to write either it is a normal number or floating point number. There are certain standard form, and these forms help us to store the number in computer in efficient manner. So let's discuss the IEEE 754 standards for floating point numbers with this background. There are two things has been given. A floating point numbers can be stored inside the machine by following single precision or double precision format. So let's first talk about the single precision format. In this format, the floating point number will be represented by using 4 bytes. 4 byte means 32 bits. So the total allowed bytes where we need to store the floating point number in the standard form, that is 4 bytes 32, and these bits are allocated like this. The very first bit, or you can say MSB, the most significant bit, will be considered as sign bit. So MSB will represent the sign, okay? So if this bit is 1, that means the number is negative. If this bit is 0, that means number is positive. 1 will represent negative number and 0 will represent positive, right? Now the next 8 bit from the MSB side, I'm saying MSB side, from this side, the next 8 bits in single precision format will represent the exponent. So what is exponent? As I have given you the previous example, if you are writing something like 1.101011 into 2 to the power, let's say you are writing minus 8. In that case, this part will represent the exponent. Okay. So from MSB side, these 8 bits will be storing the exponent, and then the remaining 23 bit out of the 32 bit will store the mantissa. So what is the mantissa? This is the normalized mantissa. So the remaining part which is here, that will be considered as mantissa part. Okay. So this is the format when we store the number in IEEE 754 single precision format. Now let's talk about double precision format. So in double precision, the format will look like this. Total allowed or allocated bytes in double precisions will be 8. So there will be 8 bytes is equal to 64 bits. In total 64 bits, we will store the floating point number in double precision. Out of the 64, the very first MSP, most significant bit, will be storing sign, or it will be treated as sign bit. So again, if it is 1, then we treat number as negative. If it is 0, we treat number as positive. Right. Next 11 bits from the MSP side will be storing the exponent. And the remaining 52 bits will store the mantissa part. The total size is 64 bits. 1 is sign bit, 11 bits for exponent, and 52 bits for mantissa. In some of the cases, we store these exponent part by adding the bias into it. So let's talk about the bias. In both these formats, in single precision and double precision, look at this table. We have 1 sign bit. In single precision, there are 8 bits to store the exponent, and in double precision, there are 11 bits to store the exponent. In single precision, there are 23 bits to store the normalized mantissa, and in double precision, there are 52 bits to store the normalized mantissa, and bias in single precision is 127, and in double precision is 1023. So let's take an example in order to understand what is the meaning of this bias and biased exponent. Normalized mantissa, you do understand what is the meaning of mantissa and what is the meaning of normalized. The meaning here is, let's say if I take a number 0.000010101. Now when we normalize this, so we do write this thing as 1 point. This point will be shifted here, and then we write 0, 1, 0, 1, 2 to the power. It is 1, 2, 3, 4, 5, 6, minus 6. So this is the mantissa, which is normalized mantissa. Okay. Right. So I hope you do understand what is the meaning of normalized mantissa. Now let's try to understand what is the meaning of biased exponent. In case a bias is given in single precision, if we want to store this particular number, then this exponent need to be added to the bias value. So rather than storing -6, we will store 127 minus 6, and it will give us 121. So in exponent part, which is having 8-bit, in 8-bit we will store 121 value rather than -6, right? So that part we consider as biased exponent. Similarly, in double precision, the value of bias is 1024. So in case this is the number which is having exponent as -1, in double precision, in these 11 bits, we will store 1023 minus 6. So that will give us 1017. Okay. So rather than storing -6, in these 11 bits, we will store 1017 in binary. So that is the meaning of biased exponent. Now let's take an example and try to understand both these single precision and double precision in detail. So let's consider we are having a number as an example. We can take, let's say 85 point, we are having 125. This is in, we consider in decimal base 10, right? So if you convert this in binary, let's convert it into binary. So how we can convert this thing in binary? You know that the decimal to binary conversion. So you can start taking this part, the integer part, and then the fractional part separately. So here you can start finding out the binary form. Remainder will come 1 here. Then again you will get 21 here, and the remainder will be 0. And then if you divide this value with 2, you will get 10 times, the remainder will be 1 here. If you divide this thing again 5 times, and the remainder will be 0. You divide it by 2 times, and the remainder is 1. And then again we divide, so 1 times, and the remainder is 0. So we will get 1 0 1 0 1 0 1. This part, integer part in binary, will be represented as 1 0 1 0. In this manner we are writing 1 0 1 0 1 0 1. Now what about this part after the point, after this decimal point? We know that to write the number after this, we need to divide this particular value, start dividing by 2. So when we divide it, we will get 0. How much you will get? You will get 250. So that means before this decimal point still we are having 0. That means we will get 0 here. Now again we will divide this value with 2. And once you divide it, this time we will get 0.500. Again we are getting 0 here before the decimal point. Again we will get 0 here. Still we keep on multiplying this thing with 2. So if we multiply this value with 2, then this time we will get 1.0. maybe a number of zeros are here. So now we will get 1. That means this 85.125 base 10 will be converted into binary like this. So let me clear this. I hope this conversion is clear to everyone. Now once you have this, you need to write it in the standard form. So what is the standard form? In the standard form, you write this thing as 1.0101010001, and then 2 to the power 1 2 3 4 5 6. So this is plus 6, right? So this is the normal form in which you are writing. In that case, this is the exponent, so the value of exponent is 6. In case you are storing this number in single precision, so I'm writing, let's say, single precision. So in case we are representing this in single precision, because this number is positive, so sign bit will be 0, and remaining 8 bits for exponent. And if your exponent is biased exponent, in single precision the value of bias is 127. So this exponent, which is having value 6 here, that will be stored in biased exponent. We have to add 127 to 8. So we need to store in 8 bits. This will give us 133. Right. So if we convert this 133 into binary, same process you can follow, or otherwise, when you want to represent this 133, how you can represent? So you can have 8-bit representation. So the very first bit is 1, you can set, because in 8-bit, if positional representation, if you do, let me do it. So 1, 2, 3, 4, 5, 6, 7, 8. Let's say there are 8 bits. This bit positional value is 1. This will have 2. This will have 4, 8, 16, 32, 64, and 128. So in case if you want to represent 133, this one, once you set, it is 128. In 128, if you add 5 more, this one and this one, you will get 133. So the remaining places you can set 0, right? So you can convert 133 into binary like this. So that means your biased exponent in 8-bit, you will store 1 4 times 0, then 101. So your biased exponent, you will get 1 0 0 0 0 101. Let me clear it. So this is your biased exponent. Now after the biased exponent, you need to represent the normalized mantissa. So your mantissa is this. This portion is giving you mantissa. The next is normalized mantissa. Mantissa need to be stored in 23 bits. In single precision we are talking about, so there are 23 bits in which we need to store the mantissa. And mantissa is having this. So mantissa is having 0 1 0 1 0 1 0 0 1 1 2 3 4 5 6 7 8 9. So these are 9 bits. We need to set 23 bits. So if we want to make it 23, we need to include 14 zeros. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 zeros. So altogether this is having 23 bits mantissa. So the overall number in single precision IEEE format, representation, the final representation of 85.125 will be, so sign bit is 0, that is 1 bit. After sign bit, 8 bit represent exponent. So that exponent part is, let me change in color, exponent part is this, so that is 1 0 0 0 0 1 0 1, that is exponent. And the remaining part is mantissa. So the mantissa is this 0 1 0 1 0 1 0 0 1, then 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. So you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So this is extra. So just I'm cleaning the last. This is the representation of this given number 85.125 in single precision format. This is the representation in single precision. This is the representation in IEEE 754 single precision format. Right? If we want to represent same number in double precision, if we want to represent the same number in double precision, then how we will represent? So let me clear this. I'm just clearing this. Sign bit will be 0 only. Here I am writing double precision. So in double precision, sign bit will be 0 because number is positive. It is 85.125. After the sign bit, there is biased exponent, and in double precision, biased exponent having 11 bits. So your exponent and the value of bias in double precision is 1023. So in this case, this value of exponent 6 will be added with 1023. So 1023 plus 6 will give us 1029. And when you represent this 1029, again you know that how you will convert this 1029 in binary. It is very easy. So 1029, it will be represented with 10 bits or 11 bits, let's say we are taking. So the 11th bits, okay, so if I represent 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bits. This is actually 2 to the power 10. So 2 to the power 10 is 1024. So this is 1. The place value I'm saying, the weight of this place. This is 2, 4, 8. This will represent 16, 32, 64, 128, 256, 512. So I want to represent 1029. So this bit, when I'm setting high as 1, it is giving me 1024. In 1024, 5 I need to add. So this is and this is will give me 5, and the rest of the places I can set as 0. So this will represent me 1029. That means this is the value of biased exponent. So that is 1. So let me write in different color. Biased exponent is 1, 0, 0, 0, 0, 0, 0, 0. So there are 7 times 0. There are 7 0, and then 101, 101. So these are the 11 bits, right? Now let's clear it. Now we need to represent normalized Mantissa. The third part is normalized Mantissa. And this normalized Mantissa we need to represent in remaining 52 bits. So the Mantissa part is 0, 1. Then remaining bits you will set as 0. So you are having the part like 0, 1, 0, 1, 0, 1, 0, 0, and 1. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. Then remaining how many bits? You require 43 bits. So remaining 43 zeros will follow. like this. So this bit pattern of 52 bits will represent the normalized Mantissa. So if you want to represent the overall number in double precision, the very first bit will give you 0 as sign bit. Let's say I'm representing the very first bit as 0. Remaining 11 bits will give you 1, 0, 0, 0, 0, 0, 0, 7 zeros, 7 times 0, and then 1, 0, 1, 1, 0, 1. Then remaining 52 bits. This will be the representation of given number in IEEE 754 double precision format. Okay. So I hope with this the IEEE 754 standard of floating point number representation is clear to you. Closing this lecture. Thank you everyone for coming.